Stan Gibilisco here to talk about Ohm's law. I just want to describe for you very briefly what that law is and how it works in a simplistic sense. Ohm's law generally applies to direct current circuits, DC circuits. Sometimes it applies to alternating current circuits, but not always. Let's look at a very basic DC circuit. Any DC circuit can be broken down into a source of voltage E, a resistance R, and then a current that flows, which we denote I for intensity. That comes from the French word for intensity of current. That's where the I comes from. Normally, we would measure resistance or express resistance in units called ohms. We would express current in units called amperes or amps, and we would express voltage in units called volts. The E for voltage, by the way, is the mathematical variable symbol for it, which refers to electromotive force. Electromotive force, just a fancy term for voltage. R, resistance, as a mathematical variable in ohms, sometimes symbolized like this, and current in amperes, usually symbolized as A. The ampere, the unit in amperes, is symbolized A. The current as a mathematical variable will be symbolized as I. Ohms of resistance is either written out or symbolized like that. Voltage, volts is symbolized V. Voltage is symbolized E. So you got that straight? Sometimes voltage is symbolized as the V, however. Well, anyway, in a circuit like this, you might get the idea that the amount of current depends on the voltage and the resistance. You might get the idea that if you have a certain resistance and you increase the voltage, you'll get more current. And if you got that idea, you are absolutely right. You might get the idea that if you have a certain constant voltage and you decrease the resistance, you will also get more current. And again, if you got that idea, you are also right. In fact, current in amperes equals voltage in volts divided by resistance in ohms. And that is the formula that you will usually see as the fundamental formula for Ohm's law. The current in amperes equals the voltage in volts divided by the resistance in ohms. So if you have, for example, a 6-volt battery, a 2-ohm resistor, your current is going to be 6 over 2 or 3 amperes. If you double that voltage to 12 volts, then you will get 12 over 2 or 6 amperes. So the current will be directly proportional to the voltage if you leave the resistance constant. If you increase the resistance, the current will go down, and we say therefore that if you leave the voltage constant, then the current is inversely proportional to the resistance, meaning that as the resistance goes up, the current goes down. If the resistance doubles, the current gets cut in half. If the resistance triples, the current goes to 1/3. If the resistance increases by a factor of 100, then the amperage or current will go down to 1/100th of what it was. Now we can rewrite this formula using simple algebra to express voltage in terms of current and resistance. We simply multiply through by resistance and we get the formula E equals I times R. Voltage equals current times resistance. We can also manipulate this formula to get resistance in terms of voltage and current, and when we do that, we get R equals E over I. So you might sometimes see a triangle, what they call an Ohm's law triangle. Like this. If you see this triangle, you may have seen this as a sort of a memory aid. Voltage equals current times resistance. You blot out the I, and you get current equals voltage divided by resistance. You blot out the R, you get resistance equals voltage divided by current. I'm not real fond of this particular memory aid because I think it's better to actually realize this formula while you imagine a circuit like this, a source of voltage, a specific resistance, which includes, by the way, the resistance of the wires and the resistance that may exist inside of the meter and the resistance that may exist inside of the battery. So this resistance is actually the total circuit resistance. So that is Ohm's law for DC circuits, direct current circuits. Stan Gibilisco signing off. Until next time, so long.